Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Steve Greenbaum, who is a professor of physics at Hunter College in the City University of New York and a fellow of the American Physical Society. Professor Greenbaum's main research interest involves spectroscopic studies of disordered solids by magnetic resonance and synchrotron X-ray absorption, most of which has recently centered on materials for electrochemical energy storage and conversion. He has authored or co-authored over 260 peer-reviewed publications and given over 60 invited talks at national or international conferences. Welcome, Steve.
Thank you very much, Gil. Thanks for the kind introduction.
Sure, yeah. So you are a well-known expert in the area of batteries, and conceptually a battery is simple, two electrodes and an electrolyte in between. But there are so many different materials we could use, right, for both the electrodes and the electrolyte, and they have advantages and disadvantages. So what's the state of the art? And obviously it depends on the application, I would imagine, from automobiles to laptops to increasingly mass storage with solar and wind powered modalities. So what's the state of the art in terms of battery design and construction?
Oh, okay. Well, batteries have been with us for a long time, and for many years we just take for granted for our portable devices. We could just go into Radio Shack or I guess CVS and replace our batteries. These are, the commonly used alkaline batteries. But of course, I think even now the general public is aware that batteries are much more sophisticated and powerful now. In fact, also that there's a growing need to make them better and safer. So I guess the most common and well-known battery is a lithium-ion battery, right? A lot of positive publicity. I mean, the 2019 Nobel Prize in Chemistry was awarded to 3 individuals for the invention and development of the lithium-ion battery, and that is really at this point I think we're taking for granted that
was from the 60s, right? The discovery was.
That's correct. So I mean, actually, I know 2 out of the 3 individuals fairly well. Stanley Whittingham at the State University of New York, Binghamton, and John Goodenough at the University of Texas. Stan did some very groundbreaking work when he was a scientist at Exxon in the 60s. He was really the first to demonstrate that you could have basically a lithium intercalation reaction. I think he was using titanium oxide or titanium sulfide. Now the battery didn't actually, was not developed much further than that, but he was really the person who demonstrated that definitively. And of course, John Goodenough is very well known for his development of the positive electrode, the transition metal based like cobalt oxide so forth, and other transition metal oxides. The other fellow, Yoshina from Japan, really put it all together in terms of having the other electrode, which is basically graphite. And this is called a rocking chair configuration, where the lithium ions actually go back and forth between these two insertion electrodes, one graphite and the other a transition metal oxide. And in fact, this is actually, if you don't get anything else from this podcast, you'll know why. You'll at least know why it's called the lithium ion battery, right? Because there's no free metallic lithium in there. The original batteries, there are certainly lithium batteries based on lithium metal, but they're not rechargeable because it's very difficult to get the lithium to come back to its original flat configuration. And normally what happens is you get these mossy and dendritic deposits of lithium that eventually reach across the cell and give you a short circuit. Then you have your fire and explosion and so forth.
So when you charge, Steve, essentially there is a transport mechanism of the lithium ion from one electrode to another, and correspondingly there are electrons going through the circuit, and that's how we get that's how we are supplying the power to the battery. And then when we reverse that, lithium ions are coming back, and then we're getting the electrons back. That's how it is.
That's correct. So just to reiterate what you said, the electrons move external to the battery through the circuit between the electrodes on the outside of the battery, and inside the battery, the lithium ions need some kind of medium, and that's the electrolyte, essentially, that the lithium ions move between the electrodes. Yeah. Again, for lithium metal, when you charge the battery, instead of forming nice flat array of lithium in the original form, you get these other undesirable forms of lithium that eventually can short circuit the battery. So that's why graphite is used as an intercalation host for the lithium ions. Right? It's really a safety issue. The graphite itself, because it's there, it detracts from the overall energy density because it doesn't actually store energy in itself, but it's really a vessel for the lithium and to keep it safe. Yeah. In my own interest, of course I'm interested in all the aspects, but my major research activity has been on what I call the electrolyte bottleneck. The electrolytes we have now, which support the transport of lithium ions between the electrodes inside the battery, is an organic liquid, basically, which has almost the same energy density as kerosene. If you have a thermal event like a short circuit, there you have your fuel. And when you see these battery fires, it's the electrolyte, these liquid carbonate electrolytes that are actually burning.
So that's what was happening to that Galaxy phones, Samsung.
That's correct. Yeah. I think I guess we learned, certainly Samsung did. We learned a lot about the various issues. The thing is that in my opinion, we're really approaching the limit of how much energy we can store in a restricted volume using the same chemistry. Now, when a company, there's enormous competition, obviously, between companies to have a longer lasting battery and so forth. So sometimes I won't say they can cut corners, but certainly when you're already close to the limit, any little tweak that you do might cause a problem, and that's what resulted in the recall of all those Galaxy 7s.
Yeah. So the one of the issues, as you say, is the electrolyte. It's unsafe where if the temperature gets above certain level, or if there is some kind of a fault in the manufacturing or something like that. So the flammability of the electrolyte is something that I guess a lot of innovators were trying to avoid. So there is also electrolytes that uses soluble stuff in water instead of the organic compounds.
Aha, yes. Actually, excuse me. I was actually privileged to work on some of that material. There's a group a pretty well-known group at the University of Maryland, and they also work with the Army Research Laboratory in Adelphi, Maryland, and I've known these folks for a number of years.
Yeah.
They pioneered these ultra concentrated aqueous, aqueous solutions,
Right.
with maybe 21, 22 molar. I mean, the stuff looks like a syrup because there's just so much salt in there.
Yeah.
But there was the innovation in that regard was that normally when you have an aqueous electrolyte, you can't go above 1.3 volts, because that's the potential at which you basically you decompose the water, right? You have electrolysis of water at about 1.3 volts or so. And if you limit the voltage, of course, you're going to limit the energy density severely. So much to the surprise, I think, of the group at Maryland, a number of years ago, they found that if you have really high concentration of salt, you can actually raise the so-called electrochemical window above about 3 volts. So you can actually make close to a 3-volt battery, because the high salt concentration somehow inhibits the electrolysis of water. So and there's been a lot of work on that, and we were privileged to publish a couple of papers with this group as well.
And so the aqueous electrolytes, are they in commercial products, or
I don't think,
it still being
I don't think they're anywhere close to being commercial. I mean, certainly, I mean, if you want to talk about aqueous batteries that are commercial, of course, your lead acid battery uses them. Okay, but if we're talking about lithium, no, they're not. They're very promising at this stage. They're probably more of a scientific curiosity than they're close to commercial development. There are a number of issues involved. First, of course, you can't use them with metallic lithium because you still have that water in there, and there are other issues, even economic issues. For example, the salt that has been most studied, that forms the electrolyte when you put it in a solvent, is something called LiTFSI, and at the concentrations that they're envisioning, that a lot of the work has been done, it turns out that if you have to use that much salt in a battery, that could be economically somewhat, maybe not prohibitive, but maybe not that attractive.
Right, and then there is increasing attention to the solid state electrolytes, right? Which has obviously, from a practical perspective, a lot of advantages, but still density, cyclability, all those things need to be improved. Is that the issue?
A lot of attention. Well, I was trained in solid state physics, so I have an intrinsic interest in ionic conduction in the solid state, which is a really fascinating process. And these solid electrolytes have been known for many years. And there's a lot of effort, huge number of startup companies, plus a lot of the big car companies like Toyota, for example, have significant R&D programs using these so-called ceramic or glassy electrolytes, which are rigid solids, but the ions move inside these rigid solids by some kind of nanoscopic hopping mechanism, subnanoscopic, and it's a fascinating process. But there are a lot of challenges to make a practical battery, because these materials are very brittle, right? So it turns out that, of course, when you charge and discharge a battery continuously, you get some, modest or not so modest, in some cases, volumetric changes in the battery. It expands and contracts with charging and discharging. And if you've got a brittle electrolyte, then the interface between the electrolyte and the electrodes can be compromised, right? So you lose contact after many cycles. That's one of many, one of several significant challenges to make the solid work. You've got to make it very thin. It's very difficult to make thin. The idea is that it's the energy storage, the energy density comes from the reactions in the electrodes, right? The electrolyte is the medium which transfers the ions, right? So the electrolyte itself does not have energy density associated with it, so you want to make it as thin as possible. And that's also a big challenge to do with these solid state materials. So what I just described was the so-called ceramic or glassy solid electrolytes. There's an equally impressive and I would say massive effort on polymer electrolytes. Now this, I must reveal my bias. most of my research probably has been in polymer electrolytes for the last quarter of a century, I suppose. And there are a lot of advantages to polymers. So the two main advantages I can cite right now are they're a little softer, and they can maintain a good interface between the electrodes and electrolyte, and therefore they can essentially breathe with the battery as it expands and contracts. They're also very easy to process in very large area films, right? Basically, the various processing tools of the plastics industry that can essentially be used for the polymer electrolytes. You can make these large sheets and then incorporate them into battery production devices. The shortfall of the polymers is that the ionic conductivity, the ions don't move as well in these polymers as they do in the other solids. Okay, and that's been an enormous source of frustration for many. I think that well, let me just mention the main actor in this field is a material called polyethylene oxide, right? And that's been the star of I guess the main actor in terms of polymer electrolyte development. Many papers, thousands and thousands and thousands of papers dating back to 1980, even a little bit before. But they still haven't solved the problem. When I give talks at meetings, one of my favorite quips is polyethylene oxide. We just call it PEO. One of my favorite quips is PEO has been great for making PhDs. Right. So a lot of tons and tons of papers. There is, to my knowledge, there's only one practical battery that's based on PEO, and that's the French company Blucar, where they actually use a lithium metal and lithium iron phosphate electrodes and a polyethylene oxide electrolyte. But the ionic conductivity in PEO only becomes appreciable at higher temperatures. So this battery has to run at about 80 degrees Celsius. Right? So that's a deal breaker for many applications.
Right. Yeah, I also read that there's something called quasi-solid state electrolytes. They call it gel polymer electrolytes. Is that something that is that's coming up, or something that hasn't really gone anywhere?
It's been around for a while. Okay, so just a quick review. Inside a battery, you have a commercial lithium-ion battery. You've got this thing that separates the electrodes. That keeps them from touching each other, and that's strangely enough called the separator. Right. So the separator is a porous polymer which is soaked with the liquid electrolytes. It's kind of spongy material. It physically separates the two electrodes and also contains the ion conducting medium, which is the liquid electrolyte. Right. So a gel electrolyte is a little bit different than that. Gel electrolyte is basically you take a liquid electrolyte and you add these agents that make it into kind of more of a solid form. So there's been a lot of interest in that. To my knowledge, I think Panasonic, in what they call their polymer lithium polymer battery, the electrolyte is kind of like that. It's a liquid electrolyte that's been gelified, right? You've added sort of thickening agents, and it's maybe marginally better than the standard liquid electrolyte that's soaked into this porous separator.
So from a commercial practical perspective, we are still on lithium ion with organic electrolytes, right? That is what is.
That's correct. I would be remiss if I didn't mention that people are looking at alternative liquids. So for one promising area is these so-called fluorinated carbonates. If you replace some of the hydrogens by fluorine, you can improve the safety issues. Of course, that's a very expensive process, right? So none of this is going to work at a successful commercial level if the materials are too expensive, and that's one of the barriers right now. But a lot of people are working on these fluorinated polymers. Also, one thing that amuses me frequently is basically the efforts that people will go to just squeeze every last milliamp hour per gram out of that battery. So for example, the basic liquid electrolyte, which is a mixture of these liquid carbonates with a lithium salt dissolved in it, that hasn't changed very much in the last almost quarter century or so, right?
Yeah.
But there have been a lot of tweaks. People add these agents that form these protective layers on the electrodes, and you know, every so often you find one that's you'll see 100 papers published on this one particular additive that seems to improve things. You know, I think the most amusing thing to me is that people are actually sometimes adding fire retardants, these phosphate compounds, right? So when you start adding fire retardants to the liquid electrolyte, I think that's the wrong approach.
So what is in the typical electric automobile? Is it also lithium ion?
Yeah, that's right. I mean, the very early generation of cars, electric cars, used nickel metal hydride. Soon it was realized that you can get much better energy density with lithium ion. So that's hybrid. If you buy a hybrid vehicle today, or an all electric vehicle, or a combination, then you're gonna have lithium ion batteries, right?
Okay.
So the but again, there's always the issue of range anxiety. And the thing that keeps the car company executives up at night is the safety issue.
Right. Yeah. So presumably that is also it is carrying inflammable organic electrolyte in there in the automobile, right? And
that's correct.
Yeah. Okay.
Now I don't know what Tesla's doing. I mean, I don't know what I think. I don't know if they used to get their batteries from Panasonic. Now they make their own batteries. And of course, their specific battery chemistry, to my knowledge, is highly proprietary and secret.
Okay.
But it is it's basically a lithium ion battery, and I believe that you may, if somebody from Tesla listens to this and wants to refute me, that's fine. But I believe that they do go to heroic efforts. They have all these thousands of these cells packed into these tubes. They do go to heroic efforts to make them safe, right? Each cell has an individual sensor, temperature, and they have these means of cutting out if one battery goes into a term that's euphemistically called thermal runaway, then there's a way to isolate that particular cell and so forth. But that makes the battery pack really expensive, right? So if you could figure out a way to make these batteries inherently safe, where you didn't have to have all these individual monitors and so forth and safety issues, then that would make a huge difference, because then you could make electric cars much more affordable than they are right now.
That's interesting. So perhaps some potential artificial intelligence techniques, to look at patterns of discharge and things like that might be potentially feasible in the future.
Oh, there is. Yeah. I mean, this is an area that I'm not, well versed in for sure. But of course, there's the engineering aspect and the charge-discharge behavior and the various diagnostics. And there's the artificial intelligence and machine learning and so forth, where people can have uncovered signs that a battery is going to go into thermal runaway well before it actually happens. So these things are very positive developments, but again, this is not an area that I'm by no means an expert in.
So we increasingly have this renewable energy massive production, right? Solar farms, wind farms. Will lithium-ion technology be able to store energy at that scale at any point?
Well, that's a very good question. There are several competing technologies for storage, and lithium-ion is among them, despite its expense. But for grid type storage, you don't actually need some of the advantages. One of the main advantages of lithium ion is that you can store it in a compact space, right? Yeah. And it's not that you can save on mass and volume, and that's really good for a cell phone or for that matter electric car. But that's not really a requirement for grid storage. For stationary storage, you have these batteries stored on the ground. You don't really need the advantages of lithium in terms of volume and mass. There are other technologies that might be better in terms of affordability, like sodium, for example. So sodium chemistry is being explored a lot for these larger scale applications. Sodium is a lot cheaper, right? So sodium is a major constituent of our oceans, for example.
Right.
And you wouldn't. I don't think you'd ever dream of making a sodium-ion battery or sodium-based battery for a car, but certainly for grid storage, that's one of the that's one very attractive option. But before we leave the topic of lithium for grid storage, the fact is we have a huge amount of experience, based on all the technology that relies on lithium-ion batteries. So lithium-ion batteries are also considered in the mix in the development of grid storage.
Yeah, the good thing about the grid storage is that it doesn't really have to worry about movement, right? So I guess from a cost perspective, you can go to materials, and even from a safety perspective, since you have no movement of the device, you have less of an issue with the safety considerations, I would imagine.
Yeah, that's correct. If you look at, for example, if you look around the world, a lot of energy storage technologies rely on pumped water, pumped hydro, right? So you have to have the geography, and you have to have the local geography for that, and the infrastructure to do that. Of course, batteries are much more compact.
Yeah, the previous energy secretary, Professor Chu, I think has been a big advocate of pump storage, and I think he has recently again had something out saying U.S. should really explore pump storage as the mechanism for storing large amounts of energy, obviously. But yeah, you need to have the right geography, and then you have to also figure in, like, I would imagine, transmission losses, because it'll be highly concentrated, right?
Right, that's correct. If you want to have especially if you want to have microgrids, right? Let's say in developing countries, then you've got to have essentially battery electrochemical storage. The pumped hydro, I think, is a much greater impact on the local environment.
Right. Yeah, I mean, this is a fascinating area, Steve. It seems like it is a material science innovation area, right? I mean, there appears to be a lot of different materials that have some of these properties, combinations of those. So I wondered, if there is some kind of a algorithm that might be able to help create that optimum battery. What's your perspective on that?
Well, again, this is an area that I'm not an expert in, but
Yeah.
There's been enormous advances in computational methods where you essentially don't, we have this database of material properties, even at the elemental level and so forth. There are very powerful predictive tools for what might work. Right. I think that certainly had a major impact on development of materials, and will continue with even more powerful computation and machine learning and so forth. I think that will continue to drive further advances in material science. I myself am an experimentalist, right? So I take my cue from the battery industry in terms of what materials are interesting to them and how do they work. And so we use magnetic resonance, as you mentioned in the introduction, to understand how ions move at basically at the molecular level.
Right.
But just again to get back to your point that you just raised, we don't do this in a vacuum, right? So we read the computational modeling papers and we see how that might be relevant to materials that we'd like to study.
Right. And I want to shift gears a little bit, Steve. You've been an educator for a long time, and I know that you passionately believe in innovation at the boundaries of disciplines, but also inclusive inclusion in education. I wondered if you want to talk a little bit about that as well.
Well, thank you, Gil, for bringing that up. That is actually an understatement to say that it's a passion of mine. I'd have to say that for all these years, the thing that gives me the greatest joy and sense of fulfillment is the success of our students, right? The people that I've had the opportunity to mentor directly or just as members of my research group. It's no exaggeration to say that science is physical science in particular is extremely underrepresented among let's say Black and Hispanic students.
Yeah.
And I've been privileged to work with this population. City University is a public university, actually largest public urban system in the country. Mm-hmm. And we get a lot of first generation students. We have a lot of students from the inner city, a lot of African American and Hispanic students. And just by virtue of being there, I've had the opportunity to work with some fantastic students. One of the things I like to say in these forums when I get a chance to say them is that I certainly have never needed to make a choice between the best science that I can do and getting students from underrepresented backgrounds to be involved in research. They're as good as anybody. They're as good as any student I've ever mentored. But the really satisfying part is essentially the leverage that they get from a good science education. The difference in their lives that exposure to science at the right time can make is enormously satisfying. They get into the best grad schools or postdocs or jobs and so forth. And I'm extremely happy about that. And in the current climate, with what's been going on in the country and now I dare say around the world, the Black Lives Matter movement and so forth. Yeah. You might think it's fashionable to do this, to have more opportunities for minorities, but this has been a way of life for me for 30 years and continues to be. And I again, as I said, even notwithstanding the couple of hundred publications and so forth in conference presentations and invited talks and stuff like that, the success of these students when they get that postdoc at Caltech or whatever that is, as an example, that's really what does it for me personally.
Yeah, access makes a huge difference, right? So if you think about it from a societal perspective, segregation based on wealth used to be the case, but there is a massive segregation, I believe, based on information and knowledge, and because these are activities that span time. The outcomes depend very much on initial conditions and access. And so these cannot be really very easily corrected way down the path, I would imagine, right?
Yes, I think that's right. In some ways, I would say that I've got it easy, right? I get them at the college level, right? But I think the challenge, and now I'm not an expert at this at all, but you don't have to be an expert to know that if you don't get a kid interested in science by the time they're in 7th or 8th grade, it may be too late. So by the time they get into my freshman or sophomore physics class, they already have some direction, some interest in science and some presumably mathematical ability so they can navigate the science.
Yeah.
But we're losing an enormous population because if you don't motivate a kid to be interested in science by the time they're at least in middle school, as I said, it may be too late. Not that I haven't seen students like that who've been exposed later on as young adults or teenagers, but it's much harder if you don't get them interested early.
Yeah. The problem is everything is getting more and more specialized. There is so much information. There is so much to learn that, as you say, if you don't get people in that direction early, if those initial conditions are not there, it becomes increasingly more difficult.
That's of course
to get into it. Yeah.
right. That's true, and a lot of these things are being highlighted in our current climate, in the reaction to the police killings, and so forth, and the deeper look into how, let's say, the Black community has been treated and of course you have the enormous inequality in education. And how are you going to get a kid interested in science in seventh grade if the schools are inferior? That goes to the heart of one of the challenges, at least in my part of the universe.
Yeah. So in conclusion, Steve, I want to return to the batteries for one more
Of
time.
course.
So if you look forward 5 years, 10 years, which area and which development axis, if you will, holds the highest potential? And where do you think we will be in terms of storage, say 5 years from now?
Okay, I think that's a great question. This is a very exciting time to be in batteries. There are quite a large number of startup companies. I'm working with one of them. I won't mention the name.
Yeah.
But there are a number of these companies, and not only are they financed to some extent by the government. For example, the Department of Energy has a branch called ARPA-E, Advanced Research Projects Agency, which was modeled after the Defense Department's DARPA.
Yeah.
Very high risk and high reward type projects. So they're funding some of these startups. Plus, you have enormous amount of venture capital that's available. And I think we're on the verge of a breakthrough. It's very hard to say where the breakthrough will be, of course. As Yogi Berra once said in his inimitable way, predictions about the future. But I think I've seen some developments that look very positive. I think 5 years from now, we will probably have a working lithium metal battery, which is about twice the energy density of a lithium ion battery. It's going to be maybe a couple of years after that where the car companies are actually going to take a chance on putting lithium metal into their cars. I think it's all the electric car battery development right now is still based on improving, tweaking, and as much as you can the current design of lithium ion battery. Maybe safer electrolytes and so forth. So that's where most of the effort is. As I said, I'm biased toward the polymer electrolyte solution.
Yeah.
I think that breakthroughs are imminent in that. But not to say that my colleagues who are studying, I've done some of this too, but a lot of my colleagues are studying the ceramic glassy materials. You never know. I mean, that you could see a breakthrough in that area as well.
Yeah, I mean, it's exciting that there are a lot of different avenues people are pursuing. And do you think we will get to every home being self-contained in terms of both production and storage? So we have a truly distributed network?
No, I don't think. Not in my lifetime. I don't think we're going to see that in every single home. I mean, there are homes and communities that do that now. Actually, my son lives in Boston, and he just put solar on his house, and he's actually making money. Massachusetts actually has a very good solar program in terms of the rebates and so forth. But I don't know that I'll see that is widespread in at least the next 10, 15 years.
Okay. Hopefully, again, this is a material sciences innovation. So once a breakthrough happens, it can spread very quickly. So let's hope that we get there. So this has been great, Steve. I really appreciate the time that you spend with me, and good luck with everything that you do.
It's my pleasure, and thanks again for inviting me to participate in this forum. Thanks again.
Thank you.
Bye. Bye.